Imagine a world where we can direct molecular events simply by harnessing the power of light, stretching beyond the usual limits. But here's where it gets really interesting. What if we could make this process more flexible, more efficient, and tune it across a wider range of the light spectrum? That's exactly what the emerging science of Polaritons promises, and scientists are just beginning to uncover its transformative potential. So, what are Polaritons? Put simply, they're hybrid quasi-particles that form when photons, tiny packets of light, combine forces with matter excitations like excitons inside molecules. For years, these exotic mixed states were considered a fascinating curiosity of physics. But recently, researchers have started to realize that Polaritons might fundamentally reshape how molecules interact with light, especially during crucial photochemical reactions. And this is the part most people miss. Standard molecular charge transfer, which is vital to solar cells, photocatalytic fuel creation, and the synthesis of specialty chemicals, has always depended on fairly narrow slices of the light spectrum. Think only certain colors like green or red. Typically, a molecule absorbs light, and an electron jumps from a donor molecule to an acceptor, powering a diverse range of technologies. But what happens if you can stretch this reaction sensitivity to a much broader swath of the spectrum? That's the breakthrough reported by a team at the Advanced Science Research Center, part of the CUNY Graduate Center. In a recent study published in Nature Nanotechnology, these researchers were able to experimentally demonstrate, for the first time, a charge transfer mechanism that's both directly tunable and highly efficient, driven entirely by polaritons. Using a special category called block surface wave polaritons, BSWPs, which travel along layered optical surfaces, they found that these long-lived hybrid states are extremely effective at mediating and adjusting molecular charge transfer. Senior author Matthew Y. Sphere captured the essence of this innovation. We showed that when you confine molecules and light within a tiny space, like near the surface of a mirror, their interaction becomes so strong that they merge into polaritons, a new kind of particle that's part light, part matter. He went on to explain that by using polaritons, they could finally tune the energy needed for molecular charge transfer across green, red, and even infrared light. Previously, this idea was widely discussed, but scientists lacked clear proof it could actually work in practice. Here's the controversial twist. While polaritons intrinsically hold a lot of promise, actually capturing usable energy from them is much harder than it sounds. As Fair admitted, polaritons tend to shed their energy far faster than ordinary molecules, limiting the process's ultimate efficiency. We had to engineer all kinds of special tricks to keep the light confined and give polaritons enough time to do their job. Yet, despite these challenges, the team managed to reduce the energy required for photochemical charge transfer in a dye molecule by about 33%, a significant advancement. It's also worth noting that, in the past, optimizing these light-driven reactions required tinkering with countless different molecules to find just the right properties. Now, with polaritons, scientists can adjust the coupling between light and the same molecule, creating flexibility without starting from scratch each time. The implications are vast. This research doesn't just unveil a clever lab trick. It opens the door to more adaptable and efficient solar cells, advanced photocatalysts, and innovative optoelectronic technologies that could redefine renewable energy, electronics, and chemical manufacturing. But it raises some important questions too. For instance, if polariton-driven processes are so tough to control, is the potential payoff worth the effort? Should research funding focus more on engineering new materials, or on mastering polariton manipulation with existing molecules? And this is your chance to weigh in. Do you think the polariton approach will revolutionize solar energy and photochemistry? Or is it another scientific curiosity that faces too many practical hurdles? Could this technology disrupt existing clean energy paradigms? Or is the excitement premature? Share your perspective in the comments. Let's spark some debate on whether this breakthrough is truly the game changer it appears to be.